Hi, tonight on the Wednesday night seminar, we have Daniel Eisenstein from the astronomy department at Harvard, and he's going to tell us about mapping the universe with the dark energy spectroscopic instrument.
Okay, wonderful. So I'll be going through this talk. It's sort of about half of it is on the science motivations of DESI, and then the second half is on the actual experimental side of DESI. So I just want to give people a flavor for what's for how this works. So our goal is to map the universe with this thing called the dark energy spectroscopic instrument. And so to get into the motivation of this will work. Okay, so we'll start with the topic of the hot Big Bang. So the hot Big Bang model is the idea that the universe begins smooth and hot and dense, and then is expanding. And as it expands, it cools, which is not too surprising, but it also becomes lumpier because of the action of gravity on the perturbations. And this has been a really incredibly successful model by specifying only a small number of parameters and applying general relativity and laboratory astrophysics. We can really unify a very wide range of extragalactic observations and understand cosmology from like a second after the Big Bang until today and over a wide range of length scales. So it's a very successful model. Now, some of the most powerful tests of the model, even though the hot Big Bang is phrased as like the expanding universe, a lot of the most powerful tests come not from studying the details of that homogeneous expansion, but rather on understanding the perturbations away from homogeneity. And so when you start off, you have these little ripples and they grow over time due to gravity. And the ripples at different wavelengths grow at different rates due to the detailed composition of the universe. And this yields a really powerful set of tests. So this is very similar to receiving a birthday present. When you get a box, you don't know what's in it. The first thing you do is shake the box. And by sort of understanding how the different rattles in the box are responding to your shaking, you can try to figure out what's inside the box. And that's effectively what we're doing with the universe. We don't get to actually go out and shake the universe, but the early universe basically shook it for us. And we're now measuring the response of that over time. So large scale structure is the study of the large scale fluctuations in the universe. And I have a picture here where, can you see my cursor? Hoping you can. So
yes.
This is a picture of two long strips on the sky, back to back, where we're at the center here and going out to about a couple billion light years from Earth. And every dot on this graph is a galaxy, the location of a galaxy. And you can see that the galaxies are not scattered randomly. They're organized into big filaments and clusters and voids. And it's that is the large scale structure that we're trying to study. So when we do this, we're really doing it in a lot of different ways. We're trying to understand the physics of the early universe. We're trying to understand how structure has grown, what the physics of dark matter is. We're trying to understand the expansion history, this thing called dark energy that's causing the accelerating expansion. And we're also trying to understand how these large scale structures give rise to galaxy formation and the various properties of the universe. So when we do this, we use a lot of different probes, the galaxies, such as I showed you here, but we also study the microwave, the anisotropies of the microwave background. We study gravitational lensing. We study the presence of galaxy clusters. There's a lot of different ways we try to study large scale structure. And when I say that the Big Bang model is really predictive and helpful, is that you can specify these you can specify this formalism and actually bring together all these different kinds of observations into the study of cosmology. So when we think about cosmology, as you may know, one of the really shocking things is that the stuff that we are made of, protons and neutrons and electrons, makes up a really small fraction of the universe. So only about 4% of the mass of the universe is protons, neutrons, and electrons. And frankly, even of that 4%, less than 1% of that is bound into stars and planets and people. So we're really at a tiny part of the universe. The next bigger part is the dark matter, here labeled cold dark matter, that makes up about 25% of the universe. And the bulk of the universe today is this thing called dark energy, which is the name we give to whatever is causing the accelerating expansion of the universe, which was discovered in 1998. But honestly, we don't know what it is. I joke that when we say the word dark energy, we overstate our knowledge by a factor of 2, because all we know is that it's dark. We don't know that it's energy. So what might be the cause of this accelerating expansion? There's been a lot of different ideas put forth. The first one was the cosmological constant, which actually dates back to Einstein. But there's other ideas. It might be a new force in nature. It might be a modification to gravity. It might be some impact of extra dimensions or string theory. Like, we just don't know. And all the ideas that have been, suggested have some level of exoticism or concern. And so there's no one idea that's just so aesthetically compelling that we just pick that one and say it must be that. And so the question is, what can we do observationally? How can we try to get at this? Well, the accelerating expansion was discovered by the study of supernovae explosions and the fact that high redshift supernovae appear to be further away than we expected. And so the main way that we try to measure dark energy is by making very accurate distance measurements as a function of redshift. Measuring distance in cosmology is hard. When something's nearby, you can use your binocular vision to try to figure out distances, or maybe you're lucky and that person down the street is 6 feet tall, and so just by judging angles, you can try to figure out how far away they are. But in cosmology, the galaxies are so far away that we don't get any sort of effective parallax on those objects, and we don't really know if it's a big galaxy far away or a small galaxy nearby. So it's actually very difficult to judge distance. So, but nevertheless, that's what we need to do. So the way that I go about doing this is, and that I'll sort of describe here in the next few slides, is this idea of the baryon acoustic oscillations. So this is the idea that sound waves propagate in the first 400,000 years after the Big Bang. And this propagation of the sound waves creates a very distinctive feature in the clustering of galaxies, namely that pairs of galaxies are slightly more likely to be separated by 500 million light years than by 400 or 600 million light years. Now, it's a very weak effect, but there's just a slight tendency of galaxies to have a preferred separation. And once you can then go out and map big chunks of the universe and measure where the galaxies are and measure their separations, this is a way of trying to infer. When you measure things, you can actually sort of find this pattern and thereby get an angular scale of that pattern. And once you can get an angular scale of something whose size you think you know, then you can infer distance to that thing. So it's sort of like we're given a map and we don't really know the scale on the map, but if we can measure some property of the separation of things on the map, then we can infer what the scale on the map is, and then that's how we're going to measure distance.
Okay.
Now, these oscillations are quite weak in the study of galaxies, but they're actually relatively prominent in the studies of the microwave background anisotropies. So the cosmic microwave background is light that comes to us from the Big Bang. It's the relic heat that's left over from the Big Bang, about 3 degrees above absolute zero. And as you may know, it's basically the same strength in all directions. It's almost completely uniform. But when you make exquisitely accurate measurements of the temperature, you find there are small temperature fluctuations across the sky at the level about 100 microkelvin from one point on the sky to another. And so once you remove the 3-degree black body and you just look at those little variations, you get maps like this coming from the Planck satellite. And there's a lot of structure on these maps. And what we're actually seeing in these maps is basically a baby picture of the universe. We're looking at most of this radiation has come to us unchanged from 400,000 years after the Big Bang. And so this picture, this oval is a sky map, projected somehow. And what we're really when we look out and see little hot and cold spots, is we're basically seeing density fluctuations very early on in the universe at a distance of about 30 billion light years away from us. Okay, well, when we look at this picture, there are fluctuations on large angular scales, there's fluctuations on small angular scales, but if you look, there's a characteristic angular scale, which is kind of the size of these blobs. There's a certain blobbiness to this map, which is not due to the resolution of the telescope, but is really due to the physics of the early universe. So there's a characteristic scale in these maps. the way that we analyze maps like this is we take a map like this and we break it up into the quadrupole, the hexadecapole, L equals 4, L equals 5, L equals 6, you know, basically just the spherical harmonics that you may have learned about in a electromagnetism class. And we're basically breaking things up into as a function of these angular wavelengths on the sky. And when we do that, we get to pictures like this. So this is a plot where 2 is the quadrupole on the sky, 3 would be the hexadecapole, and we're going out to the 2000 or 3000 pole. So there's lots and lots and lots of modes that are broken up here. And the thing I'm trying to draw your attention to is this big hump and then the series of oscillations. And these are these acoustic oscillations. This is basically caused by this characteristic scale in the early universe and the harmonics of that scale. So it's like we have a violin string. The violin string has a fundamental mode that's here, and then we're seeing the overtones of that mode here, 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 and so forth. So that's the acoustic oscillations that we're seeing early on. So let's dig into this a little more. So the key
Could I
idea
ask
here,
a question? What is the variable L?
L is the multipole order.
Okay. So it really is the dipole, quadrupole, and way up to very high.
That's right. That's right. And the dipole is boring because that's just caused by the reflex motion of the Earth relative to whatever the CMB is doing. So like that's just measuring velocity.
Okay.
But everything above L equals 1, the dipole, is interesting.
And then you're looking at the whole sky when you're doing the dipole.
You're looking at the whole sky.
Okay.
Yeah.
I have a question, like kind of inspired by that. Like you said, like relative to the CMB, and I've always like heard about like, you know, there being like a reference frame, I guess, for the CMB.
Yes.
But that seems like counterintuitive to everything like I know about relativity, and like I don't know, what do you have to offer insight about like why there exists a preferred frame for the cosmic micron back CMB?
Yeah, so I mean, so you're totally right that, I mean, so the theory of relativity says there's no preferred, that you can do physics in any reference frame. But once you have material, that material does have a preferred rest frame. And so the CMB, there is a velocity boost or an inertial frame where the CMB is going to look more isotropic. And that frame is effectively very important because that's the frame that sort of all the material has managed to arrange itself to inhabit, because basically matter was scattering off radiation at early times. Okay, so we're going to go back to a time 400,000 years after the Big Bang. This is an epoch that in cosmology is called recombination, but actually should just be called combination because it's the first time that anything actually combined. So the important thing about this time is that this is a time when the universe is 1,000 times smaller, 1,000 times hotter, and 1 billion times denser than it is today. And at those early times, the temperatures are high enough that all the hydrogen in the universe is no longer able to stay neutral. It gets ionized. So prior to this time, you don't have a gas of hydrogen and helium. You have an ionized plasma of hydrogen and helium nuclei and electrons. So this time is very important because it's the time when you move from being a plasma to being a gas. The reason that it's very important that it's a plasma is that photons in a plasma cannot travel very far before they strike a free electron and scatter. And so if you have some plasma and with photons mixed in it, and you squeeze the plasma down, then the photons are actually trapped inside that region because of their short mean free path. And effectively, they're like in a region that has compressing walls. And they basically, as they scatter off the walls, they're getting blue shifted. And this increases their energy and their radiation pressure. So basically, when you're in a plasma, as you squeeze the plasma, some of the energy of the compression is actually going into the photons. Well, the photons provide an enormous amount of restoring of radiation pressure, and they actually are pushing back and halting this compression and then causing that region to expand outwards. It actually overshoots, becomes too cold, and the photon pressure drops, and then the rest of the universe pushes back, and the whole thing sits there and oscillates. So this really is exactly the same as a sound wave. The only difference from everyday normal sound waves is that the restoring force is not the random motion of the molecules in the gas, but rather the radiation pressure of the photons that are trapped in the gas. So what this means is that at early times, if you set up density or pressure fluctuations, then those are just going to oscillate like sound waves. It's really just like setting up some universe where there's just like a whole bunch of just little overpressured regions, and they all are going to try to drive these little sound waves. Okay, so after recombination, when the universe becomes neutral, now things change radically, because now photons can travel through a gas very straightforwardly, and that's why we can see each other now. And that means that now if you take some of that gas and you squeeze it, the photons just leave. They don't want to, they're not being compressed, they're not being pushing back again, resisting anything. And so that region will just continue to collapse due to gravitational instability, and the photons don't care. Okay, so when we think about these sound waves, now they sort of get a sense of like why these are important. We should imagine that if you imagine a universe that starts off homogeneous, but with some small little overpressured region, then that overpressure tries to equilibrate by driving a spherical sound wave out into the ambient medium, just like popping a balloon sort of allows a sound wave to get released out from it. And that sound wave will travel out at the speed of sound, which at these early times is fantastically high. It's relativistic, 57% of the speed of light. But that sound wave will travel until the pressure of the photons is decoupled from the gas. And at that point, the sound speed in the gas plummets by 100, factor of 10 to the 5, and the wave stalls in a spherical shell. And that shell then expands with the rest of the universe. But the main point is that you have this drop, this shell that gets formed. So now the region that was initially overpressured is overdense as well, and it has more dark matter. It's going to form more galaxies. But the region where the sound wave has ended up has more gas, and so it will also form more galaxies. And so the regions that are good at forming galaxies also create this sound wave echo that enhances the formation of galaxies 500 million light years away from it. And that distance is just the distance that the sound wave could travel. So the reason that this is so compelling for cosmology is that this distance that the sound wave could travel is something we can compute really easily. It just depends upon the speed of sound and the propagation time. And it turns out that we can infer these two quantities really accurately from the microwave background data. And so we can calibrate this length scale to about 0.3%. This is a marvelous thing, because in astronomy, we are usually arguing about distances. We just really have a hard time controlling distances. Cosmologists spent the second half of the 20th century arguing about a factor of 2 in the distance scale. And now we're saying, oh wait, there's this object, there's this property of the universe that we actually can calibrate to 0.3%. So it's immensely useful. Then the idea is that we can then use this as an object whose length we know when we go to study not only the CMB, but also galaxy surveys. And when we can measure it in populations of galaxies at different redshifts, different velocities away from us, we can infer their distances and thereby measure distance as a function of redshift. Now, the actual story is more complicated, because it's not just that one spot in the universe has some overpressure that drives something and makes it look like a bullseye. What's really happened is that every part of the universe has a vote about whether it starts off overdense or underdense. And every part of the universe has driven out a spherical sound wave. And what we're looking at is this really complicated, problem. Like, it's not that you just throw one pebble in the pond and watch the ripples. It's that you grab an entire bucket of gravel and throw that in the pond and have to figure out from that pattern what the characteristic scale is. But okay, we can go and do the statistics of this. It creates a small feature in the correlation of galaxies. And so to measure this, we need very large maps of the universe, because 500 million light years is a large scale, even for cosmologists. We're used to talking about large scales, but this is actually still a large scale compared to the scale that forms galaxies or forms clusters or whatnot. It's a big scale, and we're looking for a weak effect. So we need many examples of that scale. And that means that we have to map really large chunks of the universe. So the way that we try to map the universe is with galaxy redshift surveys. And the idea here is you start off by making an image of the sky. And from that image of the sky, you find where some galaxies are. But that only gives you a two-dimensional map of where the galaxies are. To measure the third dimension, we need to do spectroscopy in order to measure the Doppler shift of the galaxies. And this uses something called the Hubble law, that velocity is related to distance. Now, that does not, when you measure the velocities, you're not getting really, you're really getting it's like you're ordering the galaxies by distance. You don't actually know the distance to them, but you're ordering the galaxies by distance. And so we can then use this to make these maps. So the largest 3D maps use about 1 million galaxies. And this is an example from the Sloan Digital Sky Survey, but that I showed you before. But this is what we're doing. So to get, and just to sort of give you a pretty picture from this, so this illustration is sort of showing, okay, here's a small chunk of the survey where on 2D on the sky, we've found some galaxies that we think are about 6 billion years from Earth. And when you can make spectroscopy, you're going to turn this into some 3-dimensional map. And the picture I'm going to show you next is a chunk of the survey that is about the size of your cell phone camera. If you like pointed your cell phone camera at the sky and integrated for a very long time, you would see a picture like this. But I've now color coded it so that the yellow points are about 6 billion years from us, 6 billion light years from us, and the red points are about 6.5 billion light years from us. And so we get this picture, and you can actually see the large scale structure here. So this is 6 billion light years from one side to the other. But when you look at it, you'll see that the yellow points are not at the same location as the orange points. They're not at the same location as the magenta points. If these things were really scattered randomly, this picture would look actually rather different. You can see some of the large scale structure. So this is just a small part of what the large scale structure of the universe is looking like, that you really have this frothy clustered pattern on large scales. And most of what you're seeing here is structure that was set up in the first fraction of a second after the Big Bang, by the, in normal theories, by the end of cosmological inflation. So these are patterns that are baked in very early on, and that have evolved due to the action of gravity and the small modification by the acoustic oscillations. Okay, so DESI is the next generation wide field spectroscopic survey. It's really building on the legacy of the Sloan Digital Sky Survey. And DESI seeks.
I have a really stupid question. So I don't actually know it's embarrassing, but I don't know what the Sloan Digital Sky Survey is.
Yeah,
so is that a collection of everybody's data or something like that?
No, so the Sloan Digital Sky Survey was a project that was conducted from an observatory in New Mexico to image a big chunk of the sky and then do spectroscopy to make these maps. So it was an organized project to map a chunk of the universe. It's remarkable because it was one of the earliest digital surveys of the sky. So it was basically what one was able to do when one finally could stop using photographic plates and actually switch to CCD imagers. So it started construction in 1990 and started taking data in 1998. And the data that we use, we finished up in 2014, but it's been going on for 20 years of using this telescope to map the sky. And
it takes forever because you're very high resolution and you're looking at everything, right? Or something.
It takes forever.
Okay.
There's a lot of objects on the sky. That's why it takes forever. The imaging, the sky is actually pretty big. So even imaging the sky takes a long time when you want to really do it properly. There's almost 1 trillion separate pixels on the sky you would like to image from the typical image quality that you can get from the ground. You can measure about 1 trillion points on the sky.
Oh, okay.
And so that takes a while. Just even though your camera has 100 million pixels, it still takes a lot of images to build up to 1 trillion.
Sure.
But then when you go to spectroscopy, it's much worse because now every one of those objects, every object you can find in principle splits itself up into a spectrum where, rainbow of colors, and you're trying to measure a few thousand different colors of that rainbow. And so you need a lot more light from each object so that you can successfully split it up. But also just you can't do that on very many objects at a time. So in SDSS started off at 640 objects at a time, which was already like, oh my gosh, this is great because it's so much more than one. And then we built up to 1,000. And so now DESI is doing 5,000 at a time. But you can sort of imagine when you're trying to build up samples of millions and you're doing them 1,000 at a time, it takes a lot of individual exposures to do it. And that just takes a long time.
So that's a terrific. So you've got 1 trillion spectra. So you multiply.
Well, no, we have 1 million spectra.
Oh, okay.
Of the brighter objects.
Okay, great. That's what I wanted to know. Yeah, thanks.
So DESI is trying to map 1/3 of the sky over a wide range of redshifts and really build up a detailed map. And it's been designed to study the cosmic expansion history and the growth of structure. I'm not going to dwell on some of the survey details here. Let me tell you more about the instrument. So DESI is what's called a fiber-fed multi-object spectrograph. So a spectrograph means that we're going to take the light of an object and split it up and measure the colors, usually in a few thousand different spectral channels. Multi-object means that we can do many objects at a time, in DESI's case, 5,000. And fiber-fed means that when you look at a chunk of the sky, the objects that you want to study are very disordered. They're kind of spread all over the focal plane in some complicated pattern. And what we actually do is we actually arrange to put optical fibers at those locations. The light from that object comes into the optical fiber, runs off the optical fiber, and comes to the organized instruments on the other end of those optical fibers. So optical fibers are basically little pipes for light, the flexible pipes. And it'd be too hard to build this instrument where you could like successfully just immediately grab the light. You actually have to reformat the sort of geometry of the light first. And we do that with these optical fibers. So basically, we have a telescope here. The primary mirror of the telescope is here. It's a 4-meter telescope in Arizona. And the light bounces off the primary mirror, comes up to the focal plane up here, where there's 5,000 little robots that can move around to be where the light from interesting galaxies and stars will fall. Once the light enters the fibers, oops, where'd my pointer go? The light enters the fibers and it runs off the fibers all the way down the telescope into the spectrograph room. Before the light gets to the fibers, you have to really correct the image. The telescope does not by itself make a good image, a good sharp image over a wide field of view. So we have these corrector optics to fix that. So DESI is a really marvelous instrument. It was designed for very high throughput and low overheads. The cost here is about $75 million, so it's a substantial facility. That's not counting the cost of the telescope. That's just the instrument. So this is a big project. There's about 600,000 individual parts that had to get ingested and quality run through quality assurance and installed. So this is a big thing, and it's a collaboration of about 500 people.
Yeah. Wow.
Okay, so it's been fully installed. Here it is at the Mayall telescope. So the Mayall telescope is this building here. The building's almost 200 feet high for scale. So it's a very large building. This telescope was built in the 1970s as the National Observatory at the time. And here's a picture of the telescope. So it's 4 meters across the white part here. And then this is when the telescope wants to move around, it's going to swivel on this big blue horseshoe. Okay, so the light path light comes in, bounces off the primary mirror, and bounces up through these 6 optical elements here to reach a focal surface here where these fiber robots are. So the corrector optics are very large. They're about 1 meter in size. So these took a long time to get built because, of course, these have to be polished to a ridiculous accuracy. Very, very exactly controlled specifications. Here's the lenses being integrated into the lens cell, and then those cells get integrated into this overall barrel. You can actually see the bottom of one of the lenses here.
Oh yeah.
So the lenses have to get positioned to some accuracy, about 50 microns, to make sure they're really in the right spot. So here's the barrel and top end being delivered to the Mayall telescope building. So we have to sort of replace the entire top side of the telescope. Here's where they're about to lift the whole contraption up 150 feet to the floor of the telescope. This was, of course, something that gets people nervous when you have $20 million of equipment on a thread. So the heart of the instrument is really this focal plane. So it's built in 10 segments. There's 10 spectrographs, each of which can handle 500 fibers at a time, 500 objects at a time. And so we build 10 petals, each of which has 500 of these little holes in it. And once you've loaded in the holes, then basically the positioners here, like each positioner is this little pencil-sized robot, which I'll show you more pictures of on the next slide. But each of these pencils is responsible for a single optical fiber. And so this all very precision, very precisely machined. There's a lot of micron level metrology to get this to work the way you want. So the business end of the fibers is here. Each fiber fibers look like this. So each fiber is a little 2-arm system. So you have one arm that's concentric, that's swinging around, but it's sort of swinging around an elbow. And then there's a second arm that's out on this elbow, able to move the other arm. So by doing this, you can move that fiber anywhere in a 6 millimeter patrol region. So pretty small.
I see.
And you can see, so here you can see this blow up where you would screw it into the focal plane here, and then you can have one motor is actually back behind that spot and is going to cause this entire top end to rotate, and then there's a second off-axis motor that will rotate and move the fiber here at the end. So on this picture, the fiber's up here, it runs all the way down here. Every one of these boards has a little electronics board and a few wires that come off that have to get controlled. And there's a lot of detail to be done here. So these were actually built by undergraduate technicians at the University of Michigan. And in the end, they work fabulously well. We get to precision of about 2 micron control of the motion from these.
And they're all independent, right? So they're
all independent. Yeah. So that's one of the nice things is when you go to move to a new field, like you can give 5,000 simultaneous instructions and they can all move. Now, the tricky part is that they can hit each other when they move. They overlap just enough that they can hit each other. So what actually has to happen is you have to give them really complicated dance instructions so they can actually get past their neighbors and get to where they want to go. So that's one of the things I've been worrying about recently. So here's a picture of the actual focal plane sort of taken through a side port of the instrument where you can see all 5,000 of these robots ready for action. You can also see some of the chips that we use to do the guiding and acquisition of the image. So when you just point the telescope at the sky, you won't be lucky enough that you're pointing where you want to be, and you actually have to we really have to get the starlight to go onto the right pixels of these detectors to get to make sure we are pointed in the right spot. So one of the tricks here is that the fiber robots don't actually know where they are. They move very precisely, but they don't know where they are. And so we actually have to measure where they are somehow. And the way that we do this is we actually backlight the fibers. So all these positioners contain a fiber which runs down to the instrument. And so what we actually do is we turn on a light inside the instrument. The light shines up out of the fibers, and we have another camera that's looking through the correcting optics at the focal plane. And so that looks like this. And so this is then 5,000 of these sources lighting up. And what we're really trying to do is watch this camera to make sure that the robots have moved to where they're supposed to go. Where are they supposed to go? Well, they're supposed to go relative to particular spots on these CCD cameras, so that we know where we're going to arrange for bright stars to fall on those particular pixels on those cameras. And if we know that if stars fall on those spots, that we're going to have our galaxy light falling down the fibers that we've set up. So it's quite complicated to get this to actually work. Right. But it now does work, and we can acquire a new field in about 2 minutes. So we can slew the telescope and get all the fibers set up and be ready to go again in 2 minutes, which is really nice.
The data rate must be huge. I mean, yeah, I'm impressed. Yeah.
The data rate's pretty big. not as big as some telescopes, but it's pretty good. So once the light has gone into the fibers, then it runs 49 meters down off the telescope. So this is basically, you know, whatever this is, 250 kilometers of optical fiber. And it goes down to these spectrographs. And the way the spectrographs work is that you have this, you have this slit head, which is sort of a vertical alignment of fibers. And the light is going to shine out of these fibers, come to hit a collimating mirror, and get turned back into plane parallel light, which then comes back, bounces off a dichroic. Some of the light goes through, other light bounces off, hits a second dichroic, some of which goes through, others which bounces off. And then in each case, the light that comes off comes to a grating, which disperses the light as a function of wavelength. And then there's cameras that re-image that plane parallel light back onto CCD cameras. So that's the way high resolution spectrographs work in astronomy, this combination of collimation, gratings, and then re-imaging cameras. Right. So this is 30 CCD cameras that have been built. Here's pictures of one of them in action. These are about the size of each of these is about the size, a little smaller than a twin-sized mattress. So they're not too big, you know, size of a nice dining table. Here's 10 of them in the lab in the basement of the telescope. Okay, so what you get when you do this, when you actually expose this to the sky, is you get 500. Well, each of the spectrographs gives you 500 streaks of light, 500 rainbows, and this is then a picture of one of these chips, and each of the vertical lines is one of these spectra, and the long sort of U-shaped traces across are features in the Earth's atmosphere, lines in the Earth's atmosphere. Everything you're seeing here almost is light due to the Earth's atmosphere. The light from the galaxies is much fainter than that. And what we need to do is actually take the light from, we have some of the fibers are looking at blank sky, others are looking at interesting galaxies. And what we have to do is take the light from the blank sky and use that to subtract off from the fibers that contain the interesting galaxies, so that we can basically subtract off the skylight. You also see all these squiggles. These are cosmic rays that have gotten through the atmosphere and hit the detectors. And you occasionally see one brighter star, like here's a brighter star. But if you know how to look at these, then you can actually start to see redshifts by eye. So this is a little enhancement here. This is a line of oxygen that is actually out at redshift 1.6. So this is a line of oxygen coming to us from a galaxy about 8 billion light years away. And it's actually strong enough that in its little narrow wavelength band, it actually is bright enough that you can see. This is a little unusual. Normally we have to subtract off the sky and kind of do things more carefully, but actually you can, you know, some of these are bright enough that you can actually see them just even without doing much data reduction. So this is just a fun example of a spectrum of a galaxy. It's that red galaxy there on the image. And this is going from 8,000 angstroms out to almost a micron. And you see this characteristic pattern here. And these are actually the hydrogen lines of a galaxy that is out at redshift 1.3. And you know, you're not familiar with, most of you are not familiar with astro, so it's hard to get this calibrated, but it is really astonishing to me that this instrument is so sensitive that we can get a spectrum of this relatively faint object in only 45 minutes of exposure time on a 4-meter telescope. It's really amazing. And the consequence of this is that DESI is enormously faster than what's gone on before. So this is an example of redshifts from just 2 nights. Actually, this is just 2 separate observations, and seeing that we are successfully measuring, you know, thousands of galaxies at redshifts of, you know, 0.5 to 1, even out to redshift 1.5, quasars out to redshift of 2 and 3. It goes incredibly faster than what we had before. A good night on DESI measures about 100,000 redshifts, and at you know, of actually interestingly faint objects. It's not even these. It isn't like apologizing for only doing bright objects. Like it's 100,000 redshifts. The most, you know, the average night on SDSS got about 5,000 redshifts, and they of objects that are brighter. So this is really a big step forward. I'll just mention quickly that my group, in addition to working on things like DESI, also works on high performance computing. So we actually have recently computed a set of simulations with our own in-house cosmological n-body code. So this is a code where you basically imagine a box, a sort of a large periodic chunk of the universe, and you put, in our case, 300 billion particles in the box, and you perturb them according to the rules of the early universe, and you then calculate the force of gravity over and over and over and over again to evolve the particles towards the late time configuration. So we were able to run this code on what was at the time the world's fastest supercomputer, the Summit supercomputer at Oak Ridge National Lab, and we generated about 60 trillion particles of n-body simulations. It's the largest n-body suite ever run. And I think it's actually larger than all previous suites of n-body simulations put together. So it was a big deal. And so this generated 2 petabytes of data products, and we've actually just put out the papers on arXiv. So if you're interested in high performance computing in the context of astronomy, I'm available to talk about that as well.
Oh.
So DESI is going full guns now. So it's we completed our survey validation period in May. That produced about 2 million spectra. The instrument's performing really well. Very happy with how it's going. I can't say that that it's flawless. Like, the nights are not dull. We do have things we try to fix, but it's going really well. The 5-year survey started May 14, and we've already observed about 1,200 separate tiles yielding over 4 million redshifts. So it's just great. Last night we got about 130,000 redshifts. It just doesn't get old. So I'm expecting the year 1 data set to already produce interesting cosmological results. And we have a nice website with lots of detail about what the project is, and also a lot of the people involved with the project. So we have a lot of very generous sponsors that have been funding this. Most importantly, the U.S. Department of Energy. So this is actually a project that's funded out of the DOE Office of Science and the High Energy Physics Division. And a lot of thanks to our collaboration. It's been a wonderful group of people to work with.
Wow.
So with that, I'll take questions.
Oh, thank you. That's impressive. Really nice. Questions?
I have a question, I guess, about the simulation part of the whole thing. Like, when you're doing a simulation with that many trillion, like, I guess, particles or so, how do you reconcile like the analytical type solutions with like the numerical type, I guess, solution? I know that maybe it doesn't make sense, but I'm imagining like that the actual physics probably evolves in such a way that's like an intractable solution. So it'd be different than like the computational solution. I'm just curious, like, what kind of problems come up?
Yeah, well, there's different sides of the problem you just voiced. So there's you're quite right that there's all these simulations have approximations in them. And in our case, the main approximation is that all we're doing is studying gravity. And so we're not including the pressure forces and the radiation forces and the magnetic forces that might affect the formation of galaxies. Now, on large scales, gravity is the dominant force. So we can do okay with that approximation. But as you get to galaxy scales, then you want to do simulations that have more of that fine scale detail. You also mentioned the word analytic. And that's a different side of this. So these problems are ferociously nonlinear and very complicated. So in that sense, you don't have analytic solutions for the full glory of the situation. Like that's why we do these simulations. But there are solvable perturbation theories in certain limits. And in particular, linear perturbation theory and maybe second order perturbation theory you can do. So one of the things we do have to do is try to validate that our simulations match the predictions of those linear and second order theories. And we did have to put a lot of work into that to make sure that we were recovering those answers. And in fact, we found some interesting things there where we found that the standard methods in the field didn't always reproduce the linear perturbation theories. So we actually had to issue some corrections on that basis.
Yeah, thanks. Other questions, or one last question? Okay, but thank you, very much. Personally, I'm really
Yeah.
interested to find how you do this, and it's really, impressive that it all works. It's this very elegant kind of design, and nice to actually make this go. Okay, thank you
Well,
so
thank
much.
you. Great to see you all, and I'll look forward to seeing you another time.
All right. Okay.
Take care. Bye-bye.
Thank you so much.
Thank you.
Okay.